Shivangi Desai, your instructor for the video series of data mining and business intelligence. Today's our topic is outlier analysis. So let's get started. Assume that a given statistical process is used to generate a set of data objects. An outlier is a data object that deviates significantly from the rest of the objects as if it were generated by a different mechanism. Now, for easiness, in this video lecture, we may refer not outliers as normal or expected data, and similarly, we may refer to outliers as abnormal data. Now, in the given figure, most objects follow a roughly distribution. However, the objects in the region R are significantly different. It is unlikely that they follow the same distribution as the other objects in the dataset, and that's why the objects in R are outliers in the given dataset. Outliers are different from noisy data. Noise is a random error or variance in a measured variable. In general, noise is not interesting in data analysis, including outlier detection. For example, in credit card fraud detection, a customer's purchase behavior can be modeled as a random variable. A customer may generate some noise transactions that may seem like random errors or variance, such as by buying a bigger lunch one day or having one more cup of coffee than usual. Such transactions should not be treated as outliers. Otherwise, the credit card company would incur heavy costs from verifying that many transactions. The company may also lose customers by bothering them with multiple false alarms. As in many other data analysis and data mining tasks, noise should be removed before outlier detection. Outliers are interesting because they are suspected of not being generated by the same mechanism as the rest of the data. And therefore, in outlier detection, it is important to justify why the outliers detected are generated by some other mechanisms. This is often achieved by making various assumptions on the rest of the data and showing that the outliers detected violate those assumptions significantly. Outlier detection is also related to novelty detection in evolving datasets. For example, by monitoring a social media website, when new content is incoming, novelty detection may identify new topics and trends in a timely manner. Novel topics may initially appear as outliers. To this extent, outlier detection and novelty detection share some similarity in modeling and detection methods. However, a critical difference between the two is that in novelty detection, once new topics are confirmed, they are usually incorporated into the model of normal behavior so that follow-up instances are not treated as outliers anymore. So let's discuss the outlier detection methods. Here we present two orthogonal ways to categorize outlier detection methods. The first one, that we categorize outlier detection methods according to whether the sample of data for analysis is given with domain expert provided labels that can be used to build an outlier detection model. And based on that, there are three different methods, that is supervised methods, unsupervised method, and semi-supervised methods. Whereas in the second category, we divide methods into groups according to their assumptions regarding normal objects versus outliers. And based on that, we have three different methods, that are statistical methods, proximity-based methods, and clustering-based methods. So let's understand supervised methods. Supervised methods model data normally and abnormally. Domain experts examine and label a sample of the underlying data. Outlier detection can then be modeled as a classification problem. Now the task is to learn a classifier that can recognize outliers. The sample is used for training and testing. In some applications, the experts may label just the normal objects, and any other objects not matching the model of the normal objects are reported as outliers. Now other methods model the outliers and treat objects not matching the model of outliers as normal. Although many classification methods can be applied, challenges to supervised outlier detection includes: first, the two classes, that is normal objects versus outliers, are imbalanced. That is, the population of outliers is typically much smaller than that of normal objects, and therefore methods for handling imbalanced classes may be used, such as oversampling, that is replicating outliers to increase their distribution in the training set used to construct the classifier. Now, due to the small population of outlier in data, the sample data examined by domain experts and used in training may not even sufficiently represent the outlier distribution. And the lack of outlier samples can limit the capability of classifiers to build as such. Now, to tackle this problem, some methods make up artificial outliers. Second is, in many outlier detection applications, catching as many outliers as possible is far more important than not mislabeling normal objects as outliers. Consequently, when a classification method is used for supervised outlier detection, it has to be interpreted appropriately so as to consider the application interest on recall. In summary, supervised method of outlier detection must be careful in how they train and how they interpret classification rates due to the fact that outliers are rare in comparison to the other data samples. Now let's discuss unsupervised methods. In some application scenarios, objects labeled as normal or outlier are not available, and that is why an unsupervised learning method has to be used. Unsupervised outlier detection methods make an implicit assumption that the normal objects are somewhat clustered. In simple words, an unsupervised outlier detection method expects that normal objects follow a pattern far more frequently than outliers. Normal objects do not have to fall into one group sharing high similarity. Instead, they can form multiple groups, where each group has different features. However, an outlier is expected to occur far away in feature space from any of those groups of normal objects. This assumption may not be true all the time. For example, in the given figure, the normal objects do not share any strong patterns. Instead, they are uniformly distributed. The collective outliers, however, share high similarity in a small area. Unsupervised method cannot detect such outliers effectively. In some applications, normal objects are diversely distributed and many such objects do not follow strong patterns. For instance, in some intrusion detection and computer virus detection problems, normal activities are very diverse and many do not fall into high quality clusters. In such scenarios, unsupervised methods may have a high false positive rate. They may mislabel many normal objects as outliers and let many actual outliers to go undetected. Due to the high similarity between intrusion and viruses, modeling outlier using supervised methods may be far more effective. Many clustering methods can be adapted to act as unsupervised outlier detection methods. The central idea is to find clusters first and then the data objects not belonging to any cluster are detected as outliers. However, such methods suffer from two issues. First, a data object not belonging to any cluster may be noise instead of an outlier, whereas second, it is often costly to find clusters first and then find outliers. It is usually assumed that there are far fewer outliers than normal objects. Having to process a large population of non-target data entries before one can touch the real meat can be unappealing. The latest unsupervised outlier detection methods develop various smart ideas to tackle outliers directly without explicitly and completely finding clusters. Now let's discuss semi-supervised methods. In many applications, although obtaining some label examples is feasible. The number of such label examples is often small. We may encounter cases where only a small set of normal or outlier objects are labeled, but most of the data are unlabeled. Semi-supervised outlier detection methods were developed to tackle such scenario. Semi-supervised outlier detection methods can be regarded as applications of semi-supervised learning methods. For example, when some labeled normal objects are available, we can use them together with unlabeled objects that are close by to train a model for normal objects. The model of normal objects then can be used to detect outliers, which is those objects not fitting the model of normal objects are classified as outliers. If only some labeled outliers are available, semi-supervised outlier detection is trickier. A small number of labeled outliers are unlikely to represent all the possible outliers, and therefore building a model for outliers based on only a few labeled outliers is unlikely to be effective. Now let's discuss statistical methods. Statistical methods, which is also known as model-based methods, make an assumption of data normality. They assume that normal data objects are generated by statistical model and that data not following the model are outliers. The effectiveness of statistical methods highly depend on whether the assumptions made for the statistical model hold true for the given data. Now let's discuss proximity-based methods. Proximity-based methods assume that an object is an outlier if the nearest neighbors of the object are far away in feature space. That is, the proximity of the object to its neighbors significantly deviates from the proximity of most of the other objects to their neighbors in the same data set. The effectiveness of proximity-based methods relies heavily on the proximity measure used. In some applications, such measures cannot be easily obtained. Moreover, proximity-based methods often have difficulty in detecting a group of outliers if the outliers are close to one another. There are two major types of proximity-based outlier detection, namely distance-based and density-based outlier detection. Now let's discuss clustering-based method. Clustering-based methods assume that the normal data objects belong to large and dense clusters, whereas outliers belong to small or sparse clusters or do not belong to any cluster. As you can see in this figure, there are two clusters. Cluster C1 contains all the points in the dataset except for those in region R. Cluster C2 is tiny, containing just 2 points in R. Cluster C1 is large in comparison to cluster C2, and therefore a clustering based method asserts that the two objects in R are outliers. Clustering is an expensive data mining operation. A straightforward adaptation of a clustering methods for outlier detection can be very costly and therefore does not scale up well for large datasets. So that's it for this lecture. Thank you.